All right, boys and girls, I'm assuming this is working. Welcome to the back to the drive-through, a little 5-minute lesson here on curve sketching. Okay, there's going to be relatively no writing in this 5-minute lesson because this is truly a summary, a review. But man, look how many sections it covers. And so first, I want you to hear like a little story. I've lived through this completely. There didn't used to be all these graphing apps and devices. Graphing calculators used to be like $120 back when I could get a Big Mac for 50 cents. Now they're still $120 and Big Macs are $5. Desmos never existed. We couldn't figure out these graphs other than plotting tons of points. Keep in mind, that's what a graph is. It's all of the points that satisfy the requirements of an equation. Okay? And so these are all the different things that involve the shapes and outputs of graphs. So where are there x-intercepts and y-intercepts? You learned that in algebra. Is the graph symmetric? You started that in algebra. So x squared is symmetric. X to the fourth is symmetric. What's the domain and range? Algebra. Continuity. Started it in algebra 2 and done a lot of it in calculus, pre-calculus as well. Vertical asymptotes, same thing, dividing by 0. When is it differentiable? Well, anywhere where it's continuous. So we got to know what continuity is. Relative maximums and relative mins. These are where the graphs are changing from being increasing to decreasing. Okay, there you go, increasing and decreasing. Concavity. What's the second derivative tell us? Is it concave up or concave down? Inflection points, where the concavity changes, where the second derivative is 0. Horizontal asymptotes, the limits as x approaches infinity. These are all things that you've come to kind of understand. Maybe. Come on. Oh, come on. The internet is so slow here today. Okay, sorry, but I need to get this done. Not starting it over. This just kind of gives you an idea of where I used to be. If this function was given and I graphed it from 0 to 5, if I didn't know what I was doing, I might think it was an upside down parabola. But if I graphed it from negative 10 to 30, look at the difference. So this is the same graph with different windows. What you're looking at in the top graph is simply just this part of the bottom graph. So look at the difference. Oh my gosh. Oh my gosh. So look at the difference. So I guess the good news is in almost all of your classes, you have access to graphing these, but there is a chance that in your college calculus class, they don't give you access to a graphing calculator on this section. So that's kind of got to be like what your worst case scenario is how could I prepare to understand what a graph looks like if I didn't have the ability to graph it? Or like what kind of calculus are these systems using to understand the graphs? So take a look at this function. You got a squared function on top and a squared function on bottom. You got some things that can be factored. So let's look at all of the things we would want to consider about this function. The domain is all real numbers except for 2 and negative 2. That's what would make us divide by 0. Look at this weird range. The range is going to be hard to understand until we take a look at the graphs. You got 2 x-intercepts and 1 y-intercept. You have 2 vertical asymptotes and 1 horizontal asymptote. You have symmetry, vertical symmetry. It lists for you the first derivative and the second derivative. Notice, where's the first derivative equal to 0? Well, if the denominator or the numerator equals 0, so if x equals 0, that's our critical numbers. We don't have any points of inflection because you cannot solve the second derivative equal to 0. And so we're going to test these intervals based on our domain and our critical points, okay? So let's look at what the calculus tells us. So here we have a column for the function, a column for the derivative, a column for the second derivative, and then a description of the characteristics. Over here on the left, we have different ranges. So from negative infinity to negative 2, the derivative is negative and the second derivative is negative, which means it's decreasing and it's concave downward. There is no remarks about the actual function. At this point, x equals negative 2, all of these functions are undefined. So we're going to have a vertical asymptote there. Between negative 2 and 0, the first derivative is negative, the second derivative is positive. So that means it's decreasing, but it's concave upward. That's an interesting scenario. At x equals 0, we have a y-intercept there. The derivative is 0, which means we're going to have a critical point. Uh-oh. Didn't do anything for that. The derivative is 0, and the second derivative is positive, which means it's concave up, and it's a relative minimum. Okay? Between 0 and 2, the first derivative is positive, the second derivative is positive, so it's increasing and it's concave up. It's undefined everywhere at x equals 2, so that means it's a vertical asymptote. And then from 2 to infinity, the derivative is increasing, the second derivative is negative, so it's concave down. So now with all that information, look what this graph looks like. There it is. Look, horizontal asymptote at x equals, or at y equals 2. Vertical asymptote at x equals 2 and negative 2. Concave down from negative infinity to negative 2. Concave up from negative 2 to positive 2. Concave down from 2 to infinity. Decreasing from negative infinity to 2. Both decreasing and increasing from negative 2 to positive 2. There's our relative minimum then. And then increasing from 2 to infinity. So this is kind of what you're tasked with, and these are all the things you've learned, and you should be so proud of that. Practice some and see if you can get an idea what these pictures will look like before you graph them. Boom. Boom.